Okay, so continuing on with chapter 5, we're next going to discuss another way of expressing solution concentrations called molarity. Now, molarity describes the moles of solute per liter of solution, or written as N over V. Okay. If you need to know the volume of a solution to add in a reaction, the volume is the moles of solute over the molarity. And we can also rearrange this equation to solve for N, where N is equal to molarity times volume, where N are the moles of solute. Okay. So one way of expressing the concentration of a species in terms of molarity is to bracket the compound formula or the formula of the ion. So for example, the molarity of sodium ions can be written as sodium plus in brackets. So let's apply this idea to an example. So in this case, we're asked to determine the molarity of a solution obtained from taking 4.35 moles of potassium permanganate and dissolving it in enough water to make 750 milliliters of solution. So our moles in this case are 4.35 moles, and the volume of our solution is 750 milliliters. However, we can't leave this in milliliters. So let's convert milliliters into liters. So we know that there are 10 to the negative third liter per milliliter, which gives us 0.750 liters. Now, molarity is defined as moles of solute over liters of solution. So we take 4.35 moles over 0.750 liters. And if we punch that into our calculator, so let's get our calculators out and enter that in. So we have 4.35 over 0.750. And that in turn gives us a molarity of 5.80 molar. In other words, what this 5.80 molar is saying is that we have 5.80 moles of potassium permanganate per 1 liter of solution. Any questions on this example? Does this example make sense to everyone so far? Okay, so let's try to apply this concept of molarity to solve a problem. So let's try to determine the molarity of the following solution. And don't be shy to submit any questions or your proposed responses via the chat, or unmute and ask your question verbally. Or you can submit your responses via Canvas Quiz 5.7. So let's spend about 2 to 3 minutes on this problem, and then we'll discuss once we have a reasonable pool of student responses. And if you have any questions or any proposed solutions, don't be shy to type them in the chat. And the responses I see in the chat and Canvas so far look quite reasonable. Let's try to get a few more responses and we'll discuss in another minute and a half. So checking Canvas and the chat, almost the majority of the students in this session have responded. So let's now discuss this question. So first and foremost, we know that our moles of solute are 10.0 moles of sodium hydroxide. And we know that the volume of our solution is 1.50 liters. So molarity is equal to moles of solute over liters of solution. So we have 10.0 moles of sodium hydroxide over 1.50 liters of solution. And that in turn gives us 6.67 moles of sodium hydroxide per 1 liter. In other words, a 6.67 molar sodium hydroxide solution. Any questions on this example? Any questions on this example? Okay, so let's talk about how we can use molarity and use this idea of solution concentration to solve a little more complicated problems. So in this case, we're asked, what is the mass of solute dissolved in 2.5 liters of a 0.25 molar solution of copper 2 sulfate if the molar mass is 159.61 gram per mole? Now, copper 2 sulfate is CuSO4. Okay. So in essence, we're trying to go from liters of solution. And in the end, we want to report the grams of copper sulfate. Now, how are we going to calculate the grams of copper sulfate? What unit are we going to go through? What is our intermediate stepping stone unit? What unit are we going to go through? What is our intermediate unit? So we're starting with liters of solution. We want to calculate the grams. So milliliters, we can convert to milliliters, but it wouldn't necessarily get us that much closer to grams. We have the molarity, which has units of moles per liter. So how do we typically calculate grams? What units do we typically calculate grams from if we know the molar mass? Where are we going to get our grams from? How do we calculate mass if we know the molar mass? What units do we go through? Moles, exactly. Okay, perfect. So we're going to go from liters of solution to moles, and this time we're going to use our conversion factor of molarity. Then we're going to go from the moles of copper sulfate to the grams of copper sulfate using our molecular weight. Okay, perfect. So now that we've outlined our conversion factors, so starting off, we have 2.5 liters of solution. And we know from our molarity, we have 0.25 moles of copper sulfate per 1 liter. Okay. Now we also know for copper sulfate to go from moles to mass, we have 159.61 grams per 1 mole of copper sulfate. And that in turn gives us, once we enter it into our calculator, that in turn gives us a mass of 99.7 grams that we in turn round to 100 grams that we write as 1.0 times 10 to the second grams of copper sulfate to respect the fact that our answer should have 2 sig figs. Oops, one moment. Any questions on this example? So again, we went from liters to moles using molarity, and we went from moles to grams using our molar mass. Molarity is just another conversion factor. Any questions on these examples? Okay, so let's try to apply what we've learned to an example. So in this section, we're asked to figure out how many grams of sucrose are present in 185 milliliters of 2.5 molar sucrose solution. And don't be shy to submit your responses in the chat, submit your questions in the chat, or submit your responses via Canvas quiz 5.7.1. And we'll discuss this example in about 3 minutes. But again, don't hesitate to share any of your proposed ideas for this problem in the chat so we can discuss as a class. Otherwise, we'll discuss this example together in about 3 minutes. And so checking Canvas, we already have a few responses. Remember to convert your volume to liters and to calculate your molar mass for this problem. And we'll discuss in about another 2 to 2.5 minutes. Let's try to get a few more responses via Canvas and in the chat. So checking Canvas, I see a lot of reasonable responses so far. Let's take another minute to work through this problem and propose our solutions. And the responses I see also in the chat look perfectly correct. And then we'll discuss this example momentarily. Okay, so let's discuss this example. So first and foremost, sucrose of the formula C12H22O11. Okay, let's calculate the molar mass of sucrose. We have 12 gram per mole times 12 carbon atoms plus 1 gram per mole times 22 hydrogen atoms plus 16 gram per mole times 11 oxygen atoms. That in turn gives us a molar mass. Let's punch that into our calculator. 12 times 12 plus 22 plus 16 times 11. That gives us a molar mass of 342 gram per mole. Okay, so we're starting with the milliliters of solution. We're going to have to convert to liters. And if our end goal is to report the grams of sucrose, again, we're going to go through the moles of sucrose. To go from liters to moles, we're going to use our molarity. And to go from moles of sucrose to grams of sucrose, we're going to use our molar mass. So setting things up, we have 185 milliliters, and we know that there are 10 to the negative third liter per milliliter. Additionally, going from liters to moles, we know that we have 2.5 moles of sucrose for every 1 liter of solution. And then finally, to cap off this process, we know that we have 342 grams per every 1 mole of sucrose. And that in turn gives us a mass of sucrose of, punch that into our calculator right now. We get a mass of sucrose of 158.175 that we round to 160 grams of sucrose. Any questions on this example? Any question? Oh, no, it should stay as 158 since all of these inputs have 3 sig figs. Sorry about that. I wrote 2.50 as 2.5. Let me provide that correction just so that way we're respecting sig fig rules throughout our calculation. Okay, so any questions on this example? Any questions on this example? Okay, so let's try some additional problems. So let's suppose you want to prepare a solution. So in this case, you want to prepare a 0.15 molar solution of potassium hydroxide in water. And if you start with 40 grams of potassium hydroxide, what total volume of solution should the student prepare? So we know that molarity is equal to moles over liters. So let's calculate the moles of potassium hydroxide by taking our 40.0 grams. And we know that in 1 mole of potassium hydroxide, we have how many grams? So what is the molar mass of potassium hydroxide? Well, we take the mass of potassium, which is 39, plus the mass of oxygen, which is 16, plus the mass of hydrogen. And if we punch that into our calculator, we get a mass of 56 grams per mole. This is grams per mole of potassium hydroxide. Okay, so 40 over 56, that gives us 0.714 moles of potassium hydroxide. So then, if we know our molarity is 0.15 molar, and that's equal to the moles of potassium hydroxide, which is 0.714 moles of potassium hydroxide, we can then solve for the volume. And we know the volume is equal to 0.714 moles of potassium hydroxide over 0.15 moles of potassium hydroxide for every 1 liter. And if we punch that into our calculator, that in turn gives us a total volume of 4.76 liters that we round to 4.8 liters. Does this example make sense to everyone so far? Any questions on this example? Okay, so let's try to apply what we've learned in this example to solve a problem. So suppose you want to prepare a 0.45 molar solution of copper chloride in water. If you start with 50 grams of copper 2 chloride, what total volume of solution should the student prepare? Now let's take about 3 minutes to work on this problem. Don't be shy to message any questions or propose responses in the chat, or submit your responses via Canvas quiz 5.7.2. And we will discuss this example in about 3 minutes, or once we have a reasonable pool of student responses. So let's work through this problem, and then we'll discuss in about 2.5 to 3 minutes. And if you have any questions at all, do not hesitate to ask them in the chat or verbally. And wow, we already have some reasonable solutions submitted for this problem, but don't be shy to take your time. I'd like to hear from as many students as possible in this class during these sessions. So let's try to get a few more responses. And if you have any questions working through these problems, again, don't hesitate to ask via the chat or verbally. And we'll discuss in about another 1 to 2 minutes. So let's work through this problem. Let's discuss this problem just to provide a little more guidance, okay? So first and foremost, let's calculate the moles of copper chloride. So we have 50.0 grams of copper chloride. Let's calculate the molar mass for our copper chloride sample. So we have 63.5 gram per mole for copper, plus 35.45 gram per mole times 2 copper atoms. So punching that into our calculator, we in turn get 63.5 plus 35.45 times 2, which gives us a molar mass of 134.4 gram per mole of copper chloride. Okay, so we have 1 mole of copper chloride for every 134.4 grams. And that in turn gives us 0.372 moles of copper chloride. Now we know that the molarity is equal to 0.45 moles of copper chloride per 1 liter, and that's equal to the moles of copper chloride over the volume of solution. Solving for the volume, we get 0.372 moles of copper chloride times 1 liter per 0.45 moles of copper chloride. And that in turn gives us a volume of 0.83 liters. Always make sure you're careful with the molar mass calculation and that you're writing out the correct formula for the compound name. Does this example make sense to everyone so far? Any questions? If not, let's continue on now and let's continue to talk a little bit about soluble ionic compounds, which are interesting. So first and foremost, soluble ionic compounds dissociate to give their component ions in solution. So for example, if we have something like sodium phosphate solid, if we dissolve it in water and we generate aqueous sodium phosphate, that sodium phosphate in solution will break up into sodium plus and phosphate, which is PO4 3-. Now, the moles of ion in solution per mole of ionic compound is based on the chemical formula. So just to draw some pictures, I always like drawing pictures when I think about chemical concepts because it makes it easier for me to count. Okay, so we've drawn out our ions. And suppose we have 1 mole of sodium phosphate. In that 1 mole of sodium phosphate, how many moles of sodium do we have? How many sodium ions do we see? How many sodium ions do we see? 3. Yep, so we have 3 moles of sodium. Okay, and how many moles of phosphate? How many moles of phosphate? How many phosphates do we see? How many entire polyatomic ions do we see? 1. Okay, so taking this one step further, if we have 1 mole of sodium phosphate per liter, so let's suppose we have a 1 molar solution, then we know that we have 3 moles of sodium plus per mole of sodium phosphate. So in our solution, we have 3 moles of sodium plus per every 1 liter. Does that make sense to everyone? This idea that ionic compounds break into their component ions in solution, and the moles of ion per mole of ionic compound is based on the chemical formula. Do these conversions look very familiar to everyone? Does this ring a bell from the formula conversions that we did last chapter? So let's do another example. And let's think about sodium sulfide. So Na2S. So sodium sulfide, a picture of which is shown below. In solution, what ions are present in sodium sulfide and how many ions? Well, we see 2 sodiums. So 2 sodium plus, that's given by the subscript. And we have 1 sulfide, which is S2 minus. Okay, so in solution, if we have 1 mole of sodium sulfide in, let's suppose it's in a 1 liter box, we'd have 1 mole of sodium sulfide per liter. So in solution, however, this sodium sulfide breaks down into its ions. So if we have 1 mole of sodium sulfide per every 1 liter, we know that we have 1 mole of sulfide per every 1 mole of sodium sulfide. So we have 1 mole of sulfide per every 1 liter. Additionally, by the same logic, if we have 1 mole of sodium sulfide per liter, we know that we have 2 moles of sodium plus per 1 mole of sodium sulfide, which in turn gives us 2 moles of sodium plus per liter. So the concentration of your ions is different from the concentration of your ionic compound, and it's based on the number of ions per mole of ionic compound. Does this idea make sense to everyone? Does this make sense to everyone so far? Okay, so just to test our understanding of this idea, let's do a guided example. So a researcher made a 0.2 molar solution of sodium nitride, Na3N, and we're asked to calculate the molarity of each ion in this solution. So sodium nitride, so just to draw a picture, we have sodiums, we have 3 of them. And we have 1 nitride, which is N3 minus. Okay, so sodium nitride, whoops, one moment. Let me just change the pen color. So sodium nitride in solution will break down into 3 sodium plus ions and a nitride ion. Okay, so if we have 0.2, moles of sodium nitride per every 1 liter, we know that we have 3 moles of sodium plus per every mole of sodium nitride, which gives us 0.6 moles of sodium plus per every 1 liter. We also know, looking at nitride, if we have 0.2 moles of sodium nitride per every 1 liter, we know that we have 1 mole of nitride per every 1 mole of sodium nitride, which in turn gives us 0.2 moles of nitride per every 1 liter. So we've calculated the molarity of each ion in the solution. Any questions on this example? Any questions on this example? Okay, so let's try to apply what we've learned to the following example. So let's suppose we were looking at a 1.5 molar solution of cesium sulfate, and I'd like you to calculate the molarity of each ion in the solution. Notice you now have to rely a little bit on your nomenclature skills and be familiar with how to write the formulas from the name. So don't be shy to submit your responses in the chat, ask any questions verbally or in the chat, or submit your proposed responses under Canvas Quiz 5.8. And we'll discuss this example in about 3 minutes, and just be really careful with your formula assignment, as that's key to solving this problem. So we'll discuss this example in about 3 minutes. And if you have any questions, don't be shy to message me your questions in the chat or ask your questions verbally. and we'll discuss in about 2.5 to 3 minutes. And we'll discuss this example in about another 1.5 to 2 minutes. Looking at how everyone's doing so far, we already are seeing a reasonable pool of responses via Canvas and in the chat. Just to help everyone along, for cesium sulfate, the formula is CS2SO4. And from this, you'll have all the information, or most of the information that you need to complete this problem, just to make sure if you were stuck on the formulas that you have a chance to showcase and utilize the problem solving pattern that we saw in the previous example, now that we have the formula clearly established. Let's try to get a few more responses via Canvas and in the chat, and then we'll discuss shortly. Okay, so looking at Canvas and in the chat, we have a reasonable pool of responses. So let's now discuss this question. So just drawing a picture of cesium sulfate. I know it may seem a little bit silly to draw a picture, but I find it's easier to count things rather than just have to stare at the formula. So now that we have our rough picture established, we know that we have 1.50 moles of cesium sulfate per every 1 liter. And we know, looking at our formula, we have 2 moles of cesium plus per every 1 mole of cesium sulfate. And that in turn gives us 3.00 moles of cesium plus per 1 liter. We also know that when we have 1.50 moles of cesium sulfate per liter, that in terms of the moles of sulfate, we have 1 mole of sulfate per every 1 mole of cesium sulfate. And that in turn gives us a molarity of 1.50 moles of sulfate per 1 liter. Now, one thing that I just want to emphasize is that you only break down ionic compounds into their component ions. Please don't break polyatomic ions into their atoms. Polyatomic ions contain a set of atoms bonded together. So for example, sulfate is a discrete unit of atoms bonded together with charge that we call a polyatomic ion. Please do not break sulfate into sulfur and oxygen. Polyatomic ions are bonded together. Okay, so with that side note out of the way, any questions on this example? Any questions on this example? Okay, so let's talk next about solutions and dilution. So dilution is the addition of solvent to a solution. Now the key feature that I want you to emphasize is that the moles of solute does not change during a dilution. And we can write moles as MV, where M is the molarity and V is the volume. Now, so during a dilution, the moles solute initial equal moles solute final. So N1 is equal to N2. So to show you a picture of why that is, let's pretend for a moment we have 1 mole of solute and we dissolve that 1 mole of solute in 1 liter of solvent. Wonderful. Okay. Now let's pretend now that we are going to add another liter of solvent. Let's pretend we're going to add another 1 liter of solvent. So at the end of this process, we'd have a giant 2-liter tank, sure. But, and this is really critical, have we changed the number of solute molecules? So looking at the picture, before and after our dilution, do we still have 1 mole of solute? Did we add any additional red dots when we performed our dilution? Did we add any solute when we performed our dilution? So looking at this picture of our dilution schematic, as we can clearly see, our moles of solute does not change. We didn't add any additional solute. So we have 1 mole of solute in 2 liters of solvent now. Additionally, when solutions are mixed, the final volume is the total volume of each solution. So suppose, just redrawing our example here, suppose we start with 1 liter of solution. And let's change things up. Let's suppose that we add an additional 0.5 liters. What would our total volume be? What would our total final volume be when we mix these 2 solutions? We'd add them up. 1 plus 0.5 would give us 1.5 liters. Let me adjust the zoom view so that way it's a little easier to see. Perfect. Okay, so the V final can be written as the volume of solution 1 plus the volume of solution 2. Okay, now with these ideas in mind, the concentration of a solution before or after a dilution can be determined using the following equation. Since we know the initial and final moles are the same, and we know that N1 is equal to N2, and further, we also know that not just N1 is equal to N2, but we also know that N1 is M1 V1. Let's give it one moment. There's a small delay over Zoom. So we know that the initial and final moles are the same. We can express molarity we can express the moles in terms of molarity and volume. Give me 1 second to reset OneNote. Okay, so we know that the initial and final moles are the same. We can express the moles in terms of molarity times volume. So we know that the initial molarity times the initial volume is equal to the final molarity times the final volume. So from this expression, we can figure out the molarity of a solution, either the before or after a dilution, and the volume of a solution before or after a dilution. And this only works because in a dilution, the number of moles does not change. Only the concentration and the volume of the solution. So let's show how we can apply this dilution equation to solve problems. So in this case, we have 20 milliliters of 6 molar sodium hydroxide is mixed with 230 milliliters of water to yield a sodium hydroxide solution. And our goal is to determine the concentration of this dilute sodium hydroxide solution. So we know that our initial molarity is 6.0 molar. Our initial volume is 20.0 milliliters times 10 to the negative third liter per mil. I always like to convert to liters when I handle these sorts of problems. So we have 0.0200 liters, just to respect the fact this number has 3 sig figs. Okay, we also know our final molarity is unknown, so we'll put a question mark. And our final volume in this case is equal to the total final volume. Okay, so we're going to add our 230.0 milliliters of water plus our 20 milliliters of sodium hydroxide, giving us 250.0 milliliters. Let's convert that volume in milliliters into liters. Just for consistency, we need to make sure that our units are identical so that they cancel. Okay, so now that we have our final volume in place, remembering that our final volume is the final total volume of your solution. Now that we have that in place, we're going to substitute. So we know that M1V1 is equal to M2V2. So if we're solving for our final molarity, M2 is equal to M1V1 over V2. So we have 6.0 molar times 0.02 liters over 0.250 liters, and that in turn gives us a final molarity, once we punch this into our calculator, of 6 times 0.02 over 0.250, and that gives us a final molarity of 0.48 molar. Noticing that the units of liters cancel. Does this make sense to everyone so far? So the key thing, when you add water to a solution, your final volume is the volume of water and your initial solution combined. Any other questions on this example? If not, let's continue on and let's try to apply what we've learned to the following dilution problem. So, again, we're mixing a known volume of a stock hydrochloric acid solution with a known volume of water, and you're asked to determine the concentration of the dilute hydrochloric acid solution. So please don't be shy to submit your responses via the chat or ask any questions via the chat or verbally. And you can also submit your responses using Canvas Quiz 5.9. And we will discuss this example in about 2 minutes. And checking Canvas, we already have a fair number of correct responses. Let's try to get a few more responses before we discuss in about another minute to a minute and a half. And the responses I see in the chat look perfect so far. So, as we have a reasonable pool of responses from the class, let's discuss this example. So our initial molarity is 12.0 molar. Our initial volume is 10.0 milliliters. Our final volume is the total volume of water and our solution, which is 490.0 milliliters plus 10 milliliters, which gives us 500.0 mils. Let me write that as 10.0 just so we can see the sig figs. And our final concentration is unknown. So now we have all the information we need to solve for our final molarity by taking M1V1 over V2, which gives us 12.0 molar times 10.0 mils over 500.0 milliliters. And that in turn gives us 12 times 10 over 500. That gives us a final molarity of 0.24 molar. Now, one thing to note, if your volume units are the same, they will cancel in this equation. However, I do still encourage you to convert your volumes to liters just because for many other molarity related problems, having the volumes in liters is critical to getting the correct answer. In this case, it doesn't matter as long as your volume units are the same. Any questions on this example? Any questions on this example? Okay, so let's now perform another example. Let's go through another dilution example. So if we have 200 mils of a 0.60 molar solution of KCl, and we diluted it to a final concentration of 0.10 molar, and we're asked to figure out the volume of this diluted solution. Okay, so we know that our initial volume is 200 milliliters. We know our initial molarity is 0.60 molar. Our final volume is unknown, and our final molarity is 0.10 molar. So now, looking at our equation, M1V1 equals M2V2, we can solve for V2 by taking M1V1 over M2, which gives us 200 milliliters times 0.60 molar over 0.10 molar. And that in turn gives us a final volume of 1,200 milliliters. So V2 is 1,200 milliliters that we can write in terms of liters as 1.2 liters. Does this example make sense to everyone? Any questions on this example? If not, what we're going to do is we're going to work through another example. So if we prepare, I would like you to work on the following dilution example. And don't be shy to submit any questions or responses in the chat or verbally. And you can submit your responses for immediate feedback into the Canvas quiz 5.9.2. And we'll discuss this example in about 2 to 3 minutes. Let's try to have almost everyone in the class responding, just so that way I can make sure everyone's keeping pace with the material and that and if there are any questions, I can get those addressed as soon as possible. And we already happen to see some pretty fast responses via Canvas, but don't be shy to take your time, and we'll discuss this example in about another 2.5 minutes. And the responses I see in the chat look good so far. Let's try to get a few more responses and we'll discuss in about another minute. Checking Canvas, I already see a reasonable pool. Let's give students a little bit more time to respond and we'll discuss momentarily. If there are any questions at all, really don't hesitate to ask. Okay, so let's now discuss this example. So they prepared a 0.15 molar sodium sulfate solution by diluting a 3 molar stock solution to 100 milliliters. And we're asked what volume of 3 molar stock solution is required to prepare 100 milliliters of 0.15 molar sodium sulfate. So we know our initial molarity is 3.0 molar. Our initial volume, that's what we're trying to figure out. Our final molarity is 0.15 molar, and our final volume is 100 milliliters. So looking at M1V1 equals M2V2, we solve for V1 and we get M2V2 over M1, which gives us 0.15 molar times 100 milliliters over 3.0 molar. That gives us an initial molarity of 0.15 over 3. Oh, sorry, an initial volume of 5 milliliters, which we can also write as 0.005 liters. Any questions on this example? Any questions on this example? As we see, units of molarity cancel. We're left with units of milliliters. So let's now look at a little bit more interesting questions. But before we do that, let's do one last dilution practice problem. In this, we're asked how many liters of 0.1 molar potassium dihydrogen phosphate stock solution would be required to make 5 liters of 0.5, let's do 0.5 molar, 0.05 molar solution. So our initial molarity is 0.1 molar. Our initial volume, that's what we're trying to figure out. Our final molarity is 0.05 molar. And our final volume is 5.0 liters. So solving for our initial volume, we have M2V2 over M1. That in turn gives us 0.05 molar times 5.0 liters over 0.1 molar. And that in turn gives us 0.025. Oops. That in turn, let me punch this into the calculator really quickly. That in turn gives us 2.5 liters. Okay, so let's try as a group and individually to do one more dilution problem. And let's try to answer the question, how many liters of 6 molar sodium hydroxide would be required to prepare 500 milliliters of 0.2 molar sodium hydroxide? And let's not be shy to submit our responses in the chat verbally or via Canvas quiz 5.9.2. So this is a critical skill that you need to develop for understanding solution preparation. So let's take about 2 minutes to work through this problem, and let's make sure we're completely solid on these dilution calculations, and we'll discuss momentarily. And wow, everyone's quite fast at this. We already see a fair number of responses. via Canvas. Let's try to get a few more responses over the next minute, and then we'll discuss. And the responses I see in the chat and Canvas look quite good so far. So let's now go through this example as I see excellent progress from the class so far. So our initial volume is unknown. Our initial molarity is 6.0 molar. Our final volume is 500 milliliters. And our final molarity is 0.20 molar. So solving for our initial volume, we have V2 M2 over M1. So that in turn gives us 500 milliliters times 0.20 molar over 6.0 molar, which in turn, if we enter that into our calculator, gives us 16.7 milliliters, which we convert to 0.017 liters if we're following our sig fig rules. Any questions on this example? Okay, so let's talk next about mixing ionic solutions. So if you're mixing solutions with the same ion present in both solutions, you cannot use the dilution equation. Because as we can see in this picture, when we mix 1 molar sodium chloride with 1 molar sodium bromide, are the moles of each ion constant before and after you mix the solutions? Do we have, so looking here, so in our first solution of sodium bromide, before and after we mix our solutions together, do we have the same number of sodium ions? Before and after mixing, does the number of sodium ions remain the same or different? Clearly, they're different. So we can't, right? Because we have 1 sodium, and in the end, when we've mixed our solutions, we have 2, right? So clearly, this isn't just a simple dilution. So we have to handle mixing ionic solutions just a little bit differently. Okay, so first things first, we need to convert the molarity of each solution into the moles of ionic compound. So if we have 1 mole of sodium chloride per 1 liter, and we have 1 liter of solution, we have 1 mole of sodium chloride. Likewise, if we have 1 mole of sodium bromide per every 1 liter, and we have 1 liter of solution, we have 1 mole of sodium bromide. Okay, now we need to calculate the moles of each ion in each solution. Okay, and we know that in 1 mole of sodium chloride, we know that we have 1 mole of sodium plus per 1 mole of sodium chloride. That gives us 1 mole of sodium plus. That would be an example. So continuing on this calculation, we also know that in 1 mole of sodium chloride, we have 1 mole of chloride for every 1 mole of sodium chloride. And that in turn gives us 1 mole of chloride. So listing out our moles of each ion, we have 1 mole of sodium plus and 1 mole of chloride. This is from our sodium chloride. And we also have 1 mole of sodium plus and 1 mole of bromide from our sodium bromide. So then our moles of sodium plus are equal to 1 plus 1, which gives us 2 moles of sodium plus. We add together the moles of sodium present in each of our solutions. The moles of chloride are equal to 1 mole, and the moles of bromide are also equal to 1 mole. Okay, so now that we have the total moles, we calculate the total volume of all solutions. And the total volume is equal to V1 plus V2. So we have 1 liter plus 1 liter, which gives us 2 liters total. Okay, and now that we have the total moles and the total volume, all we have to do is calculate the molarity by taking moles over volume. So the concentration of sodium would be 1 mole. We get the moles of sodium, which are 2. So we have 2 moles of sodium over the total volume of 2 liters, which gives us 1 mole of sodium plus per 1 liter. Okay. The concentration of chloride would be equal to 1 mole of chloride per 1 liter. Oh, not 1 liter, 2, since that's our total volume, which gives us 0.5 moles of chloride per 1 liter. The concentration of bromide would be 1 mole of bromide per 2 liters, which gives us 0.5 moles of bromide per liter. Does this make sense to everyone? So first, just following through, you calculate the moles of each ionic compound. You calculate the moles of each ion using the formula. You calculate the total moles of each ion. Then you calculate the total volume, and the molarity of each ion is just the total moles over the total volume. Any questions on this example? Okay, so let's do a guided example a little bit closer to what you'd see on an exam. So in this example, which is split into 2 parts, first we're asked to calculate the concentration of sodium when 0.1 liters of 0.5 molar sodium phosphate is mixed with 0.2 liters of 0.1 molar sodium cyanide. So the total volume is pretty easy to calculate. We just add up the volume of each of our solutions, which is 0.2 plus 0.1, which gives us 0.3 liters. Okay. The moles of sodium plus this time. So we're calculating the moles of sodium plus from sodium phosphate. Give me 1 second just to reset OneNote as I'm noticing a small amount of delay. Okay, so now that we've calculated the total volume, the moles of sodium in sodium phosphate. So first and foremost, we know that we can calculate the moles of sodium phosphate by taking the volume times the molarity, which in turn gives us 0.05 moles of sodium phosphate. Okay. In turn, the moles of sodium plus in sodium phosphate is equal to 0.05 moles of sodium phosphate times 3 moles of sodium plus per 1 liter. 3 moles of sodium plus per 1 mole of sodium phosphate, which gives us 0.15 moles of sodium plus. To figure out the moles of sodium plus in sodium cyanide, allow me to show you the one-line method. We have 0.2 liters times 0.1 mole of sodium cyanide per every 1 liter times 1 mole of sodium plus per mole of sodium cyanide. And that in turn gives us 0.02 moles of sodium plus. To calculate our total moles of sodium plus, we take 0.02 plus 0.15, which in turn gives us 0.17 moles of sodium plus. And now to finish off this problem, the concentration of sodium plus is the total moles, which is 0.17 moles over the total volume of 0.3 liters, which in turn gives us, when we punch this into our calculator, a final molarity of 0.57 molar. So again, we calculate our total volume. We calculate the moles of sodium in each of our component solutions. Then we calculate the total moles, and for our molarity, we take the moles over the volume. Does this make sense to everyone so far? Any questions on this example? So let's show another example of the same problem where we're asked to calculate the concentration of cyanide when we mix these same solutions. So we know that our total volume is 0.1 liters plus 0.2 liters, which gives us 0.3 liters. The moles of cyanide, there's only one source of cyanide, which is our sodium cyanide. So we take the volume of our sodium cyanide solution times the molarity, which is 0.1 moles of sodium cyanide per 1 liter, times 1 mole of cyanide per every 1 mole of sodium cyanide. And that gives us a moles of cyanide of 0.02 moles of cyanide. We can then figure out the concentration of cyanide by taking our total moles, which is 0.02 moles of cyanide, over the total volume, which is 0.3 liters, and punching this into our calculator, we get a final molarity of 0.067 molar, which we round to 0.07 molar. So if you only have an ion in one of your solutions, then this problem can simplify into just a simple dilution equation. Any questions on these examples? Any questions on these examples? If not, let's test our understanding by applying what we've learned to the following problem. So let's spend about 5 to 6 minutes working through this problem, and don't be shy to submit your questions or proposed responses in Canvas Quiz 5.10 in the chat or verbally, and I'll be happy to provide feedback. And we'll discuss this example in about 6 minutes. This is the type of example that you should expect to see on an exam, as it really summarizes all of the calculations in terms of dilutions, molarity conversions, and combining solutions. And we'll discuss this example momentarily, but I'd like to have the majority of the students in this session provide a response, just so that way you can check your work, receive feedback, and if you'd like specific feedback on your question, I'd be more than happy if you send me your response as a private message in the Zoom chat. And we'll discuss this example in about 5 to 6 minutes. And checking Canvas, we already have a pool of reasonable responses. Let's try to get a few more responses, and we'll discuss this example in about 4 to 5 minutes. I really want to see responses from everyone in this session, so that way you can get a sense of exam questions and get a sense of how to perform and check calculations for these sorts of problems. And the response I see in the chat looks good so far. if there are any questions working through this problem, don't be shy to ask. We'll give everyone about another 3 to 4 minutes on this problem, but I want to make sure we have a pool of responses before we discuss, or at least that we have some questions in the chat or verbally that I can address to help everyone solve these problems. So we're starting to get a few more responses via Canvas. I'll give everyone a little bit more time as I want to make sure that everyone has attempted and fully attempted this problem, and they have a solution that they can look over and compare to the instructor solution when we cover this example momentarily. Let's discuss in about 2 to 3 minutes. And the responses I see in the chat look good so far. We're getting a few more responses. Let's take a few more minutes. I want to see a reasonable number of responses from the class, and then we'll discuss in about another 2 minutes. And if you have any questions while working through this problem, really don't hesitate to ask. Okay, so I see a reasonable pool of responses via Canvas and in the chat. So let's now discuss this example. So first, we're asked to calculate the concentration of chloride. Well, let's first figure out the volume total. So we have 175 milliliters plus 27.0 milliliters, which gives us 202.0 milliliters, which if we convert to liters, gives us 0.202 liters. For the concentration of chloride, we have 27 milliliters of our KCl solution. Converting to liters, we know we have a 0.2 moles of potassium chloride per every 1 liter. And we know that we have 1 mole of chloride for every 1 mole of potassium chloride. Punching that into our calculator, that in turn gives us 0.0054 moles of chloride. And then our concentration of chloride is equal to the moles of chloride over the volume, which is 0.202 liters. Which in turn gives us 0.027 molar. Okay, so chloride's the easy one. Let's now look at potassium. So our volume total is still 0.202 liters. So the potassium, this time from potassium chloride, is equal to 27 milliliters times 10 to the negative third liter per mil times 0.2 moles of potassium chloride per liter times 1 mole of potassium per 1 mole of KCl. And that in turn gives us 0.0054 moles of potassium. Now let's look at the potassium from potassium phosphate. So going up and reading the problem, we have 175 milliliters. And we have 10 to the negative third liter per mil. Do not forget to convert to liters. And we have 0.1 moles of potassium phosphate per liter. And now this is really an important juncture here. How many moles of potassium do we have per mole of potassium phosphate? This is one that you have to be pretty careful about. How many moles of potassium do we have per mole of potassium phosphate? 3, exactly right. Perfect. So if we punch that into our calculator, we get a moles of potassium of 0.0525 moles of potassium. Adding it together, our moles of potassium total are equal to 0.0525 moles of potassium plus 0.0054 moles of potassium, which in turn gives us 0.0579 moles of potassium. So then our concentration of potassium is equal to our total moles over our total volume of 0.202 liters. And that in turn gives us a final molarity of potassium of 0.287 molar. Does this example make sense to everyone so far? Any questions on this example? So we have concluded our discussion of chapter 5. And now what we're going to do is we're going to transition and begin the laboratory experiment for today.